going to throw it in periodically as we go through this chapter, just so we know what I'm talking about. So a polynomial. What is a polynomial? Okay, so we have multiple terms. We are technically, we think of it usually, we use it when we have 4 or more, because if it's one term, what do we call it if it's one term? Monomial. 2 terms is binomial. 3 terms is trinomial. Polynomial is everything after that. But technically, even the monomial, binomial, trinomial, those are all types of polynomials. So a polynomial is just when we are adding powers of x together, and they can have a coefficient. A lot of times we write them in decreasing order. You will see this definition pop up periodically, and it looks a little confusing, but all it's saying is we are adding powers of x. So a sub n is just the coefficient of the nth term. X to the n power, whatever that n might be, first, second, third, fourth power. They don't have to be written in decreasing order like this, but they certainly can be, especially if we're putting it in typical standard form. If I talk about the degree of a polynomial, what am I referring to? The exponent. So the degree is the highest exponent. Okay, in my example up here, the x to the n would be the highest exponent, so it would be degree n. What are coefficients?
The number in front.
The number being multiplied with a variable. Let's say with x. So in this scenario, it's that a sub n, a n minus 1, okay, and it would just continue. So there are many coefficients that we see in here. All those numbers being multiplied with the variables are coefficients. What is a constant term?
Something without an x.
So the term without a variable. In this case, it's that a sub 0. The leading coefficient. What is that?
The one with the highest degree.
So the coefficient of the term with highest degree. In this scenario, that would be the a sub n. The leading term is the term with the highest degree. So the term is the coefficient and the variable together. Something to note, when we have this definition of polynomial, all the exponents are whole numbers. So that means when I say it's a polynomial, we know we're adding powers of x, but those powers have to be things like 0, 1, 2, 3, 4. You can't have a negative exponent. You can't have a fraction or a decimal for your exponent. Likewise, that means your exponent can't be on the denominator, because that would be, or your variable can't be on the denominator, because that would be like having a negative exponent. That would turn it into a rational function, not a polynomial. So we are looking at things with nice exponents, only positive whole numbers here. Any questions about those terms? And we will be seeing these again. It's not the only time I'm going to put them up here. When we look at the graph of a polynomial, it will always be smooth, continuous. It's just like a wave. You're not going to have any corners, so no V's or anything, no breaks in your graph, no sharp turns. So it's just a nice smooth curve. We could use transformation rules sometimes to graph them, and all of those are the same as what we've already learned. Okay, we've talked about graphing like quadratics and cubics. Those are types of polynomials. So any rules that we've already learned still apply here. So our first example, I want to look at each of these and decide if it is a polynomial. So we'll say yes or no, is it a polynomial? If it is a polynomial, we'll give the degree. If it's not, I want to tell why not. So is A a polynomial? Yes. What is the degree here? 4. Degree is the highest power. It does not have to be the first term. That's a common mistake. People only look at that first term. We have to look at all of them and just pick the highest exponent. B, is this a polynomial? No. A square root is the same thing as saying x to what power? And I told you that in a polynomial, we can't have fractions or decimals. So this is no. And the reason is because we have a fraction exponent. Or a variable under the radical would be an okay explanation as well. C is this one. No. Why? Bless you.
Because there's an exponent underneath the denominator.
Right. There's a variable in the denominator. That's essentially the equivalent of having a negative exponent, so we know that can't happen. All right, D. Is that one a polynomial? Okay, which rule does it break?
Yeah, I think
Does it have a negative exponent or a fraction exponent, variable in the denominator? No, so this one is technically a polynomial. But the degree here is a little bit tricky. Okay, degree is your highest power of x, right? Is 0 the same thing as 0x? Okay, is that the same thing as 0x squared? Yeah, it's still 0. Is it 0x cubed the same? So can you tell me what power of x has to be with that? No, it could be anything. So if it's just a 0, it actually has no degree. That's called the 0 polynomial. And it has no degree because it could be any power of x multiplied with that 0, and it's still equivalent to 0. So we couldn't name just one.
so if it specifically put that, like a certain number, like if it had 30 for the next part, you must put 30.
Yes. All right. E. Is this one a polynomial? Yes. Okay. Now let's talk about the degree. Is 8 the same thing as 8x?
Yes.
It is?
No.
No. It works up here because 0 times anything is still 0. But is 8 times x the same thing as 8? No. So what power of x would have to be here so that anything to the 0 power becomes 1. So this one has a degree of 0. Degree, another way of thinking about that is just how many variables do you have? So if we have 8, there are no variables with that. We have 0 x's with that term. All right, f. This one is in factored form. Would that be a polynomial? Yeah, if we multiplied it all out, it would look like the others. We'd have terms added together. Okay, so the degree here is a little bit different. We said the degree is the highest power of x, but that's assuming all of your terms are just added together. So that's essentially assuming we multiply it all out. So we could we multiply all this out if we wanted? Sure, and then pick the highest power of x. But we don't want to necessarily put more time into it than we have to. So let's just think, what would our highest power of x turn out to be? We have a negative 2x cubed. Okay, if you FOILed here, x minus 1 squared, we would get an x squared, right? And if you take an x cubed times an x squared, what do we get? X to the fifth. So our degree is actually going to be 5. Now, did I fully multiply that out? No. But I don't have to. I just have to think, if I were going to, what would be the highest power of x that appeared? So I had the 3 x's out in front times the 2 x's in the parentheses, so I would get 5 there. And we will practice that a lot more in this chapter. Are there questions? So here is what I want you to do. Take a couple minutes, and I want you to draw me a rough sketch of each of these. You can use a calculator if you need to, just a rough sketch. It's just your chair. We've seen that one before. Okay. What's x to the fifth look like? How is it wider?
Near 0, where like, what am I trying to say?
I don't think you even know.
I don't think I know. I know
So
what I'm trying to say, but I don't know what I'm trying to say.
let's graph them together then and compare. If we graph x cubed and then x to the fifth together. So there's x cubed, x to the fifth is the red one. So how is it different?
It's
A little
skinnier.
skinnier. Yeah, so it's the same general shape, but just as it went on, it got a little bit skinnier. What did x to the fourth look like?
Like a parabola, but flat at the bottom.
And it's a little bit skinnier than your typical parabola. And what happened with x to the sixth?
Okay.
Even skinnier. Okay. So, if we just have x to a power, we're kind of seeing it takes on one of two shapes. It either looks like the chair or it looks like a parabola, right? What decides which one it looks like? So if you have x to the n, it will resemble x squared if your power is even, and x cubed if your power is odd. As the exponent gets bigger, what happened to the graph? Yeah, okay. Let's just say it narrows. So the higher your exponent, the skinnier your graph is going to be, but the shape is generally one of those two. All right, so this leads us into a concept called end behavior. So end behavior doesn't tell us anything about what the middle of the graph does, but it tells us about the ends. So, this one's going up, this one's going down. In behavior, so it's just what's happening as your x gets really, really big or really, really small. And it is based solely on your leading term. So that leading term in a polynomial, the term with the highest degree, that's what's going to determine which way your ends are pointing. If they're both going up, both going down. All the other terms are just going to impact what's happening in the middle of your graph. So, if it would have an even degree, so something with an x squared, x to the fourth, x to the sixth, what do we know about the ends? Yeah, they're both going up as long as your leading coefficient is positive. So for end behavior, what I usually do is just draw arrows. And that's all I'm expecting from you. You might see sometimes they write it out as x goes to infinity, f of x goes to infinity, and have something a little more detailed. But we're really just talking about which direction are the ends going, so arrows are sufficient. What would happen if I threw a negative leading coefficient? So a negative x squared. Yeah, it flips it so they both go down. All right. If we have odd degree, what does it look like? Yeah, our chair, right? So the left hand side is going down, the right hand side is going up. But if I put a negative in front, so like a negative x cubed, what would that do? Switches them. So it'd be up, down. So let's practice looking at some polynomials and just deciding what the end behavior would be, which directions the ends will go on our graph. Right, so on this one, my end behavior, which term do I look at to decide my end behavior? The leading term, the highest power. So I'm looking at this one. So what's my end behavior going to be? My degree is 3. Odd looks like a chair. It's a positive coefficient, so it didn't flip, so my end behavior is down, up. Second one. So my leading term, the term with highest degree, is right here. What's the degree of that? 6. 6 is even, so it means it looks like a parabola. But I put a negative in front, so what happens to my parabola? It's both going down. All right. This one, what would I have to do first? Multiply it out. But we only really care about the leading term, right? So let's just think about the highest power of x. We have a 3. In this parenthesis, my highest power would just be an x. In this parenthesis, we would end up with an x squared. So if we multiply it all together, my leading term would be 3x cubed. What's the degree of that? 3. It's a positive coefficient, so what's my end behavior? This one. So we would need to multiply it out, except I don't really have to do everything. I just need that first term. So we have an x squared. What happens if you take an x squared and cube it? Becomes x to the 6th. Power to a power, you multiply them. This one.
Oh, that's what I'm dumb.
Sorry, did you misunderstand my question? Sorry. So if I multiply this all out, my leading term, I would have a 1/2 x to the 12th. So my degree is 12. Positive coefficient, so what's main behavior?
Up.
Did you guys understand how we did those?
Confused myself by
So the next one, I want you to take what you know about in behavior and match each of these equations with the graph. So take, what should the in behavior be for f of x? Up. So that has to be graph C. G of x, what should our in behavior be? Down, down. So that's A. H, what's my in behavior? Down, up, so that's graph B. And K, what's our in behavior? So that's graph D. Any questions on those? So we have a little more terminology to go through. Turning points are where a graph changes direction. So if I think about this graph, if I'm looking at everywhere it changed direction, it was going up, and then at this point it switched and started going down. Here it was going down, and then it switched and started going up. Going up, switched and went down. Going down, it switched and went up. So this one has how many turning points? 4 turning points. Those turning points can also be called the maximum and minimum points. Those are high and low points that happen when our graph changes direction. Extrema, that just means maximum or minimum. An absolute max or min is the highest for a max or the lowest for a min. Point on the entire graph. A local max and min is just higher or lower than surrounding points. So there might be something higher on the graph itself, but just not around that point. On the graph I drew, do we have an absolute max? Is there a point that's the highest on the entire graph? No, because it keeps going up. But I have 2 local maxes. This first one is a local max, and then this one would also be a local max because they are higher than the surrounding points. Do you guys understand the difference between the 2? So let's just practice kind of identifying some of those. So let's look at this one. So here's our graph. Identify and classify the local extreme points of f. When I say extreme, that means all the maxes and mins. So we need all the local max and local min points. Okay, so if I'm looking at f, a local max is just higher than surrounding points. Which one would that be? Let's see. What about local mins? Any others?
DH.
Now let's do the same thing for G. What about on G? Do we have a local max
Mm.
and a local min? So we see it's possible to have multiple local maxes or local mins, depending on the graph. E to H, that one's a local min, but what else would this one also be?
What's it called?
It's also the absolute min because it's the lowest point on the entire graph. So it can be both. All right, so then the absolute maximums for F and G. So graph F, did it have, we just said absolute min, the lowest on the entire graph was EH. Did it have an absolute max? No, because it keeps going up forever. So if you have arrows going up, we don't have an absolute max. G, does it have either? No. Because one end is going up forever and one is going down forever. Questions there? So I just have a couple last things to mention and then we're done for today. When we're talking about turning points, it's actually related to the degree. So a polynomial of degree n has at most n minus 1 turning points. So if it's degree 2, you can only have 1 turning point. If it's degree 3, you can have 2 turning points. If it's degree 7, you could have 6. Now notice it said at most. So degree 7 could have 6 turning points, or it could be less than that. Likewise, if I know you have a certain number of turning points, I can tell you the degree. So if I said, okay, this graph has 5 turning points, what would your degree have to be? 6 or more. Okay, if I said we have 2 turning points, it would be degree 3 or more. And the last one I'm not going to worry about right now. Those are the only 2 points I really want to touch on. The number of x-intercepts, like zeros, that's related to the degree. So we know when we were solving quadratics, how many solutions did we always get? 2, because the degree was 2. So the number of x-intercepts would be at most the degree. So if I look at a graph and it has 4 x-intercepts, that means it has to be at least degree 4. When I say at most, it may not match exactly because we know sometimes we get imaginary zeros, and when I graph those, do we actually see those on the graph? No. So those are all points that we will be working on in the coming days. Final thing that I just want to touch on to wrap up today and set us up for tomorrow. When we look at zeros, we've seen cases where they have multiplicities, right? And that meant it was a 0 multiple times. And I told you that we needed to start kind of recognizing that. When we solved quadratics, we would write M2 if it had a multiplicity of 2, because that multiplicity will change the graph. If it has an odd multiplicity, when you graph it, whatever that 0 is, your graph will just hit that and go through it. So if the multiplicity is any odd number, 1, 3, 5, 7, 9, then when we graph it, we'll just hit that point and go through it. But if we have an even multiplicity, a multiplicity of 2, 4, 6, 8, what happens is we will hit that and bounce off. Okay, so odd multiplicity will go through, even multiplicity will bounce.